Tonight, we're going to follow a signal that should not exist. 15 billion miles from Earth in a region no human will ever visit, a school bus-sized spacecraft is drifting through interstellar space. The cameras are off, the power is fading. The sun is just another bright star behind it. And yet, across that unimaginable distance, Voyager 1 is still whispering back a message that does not fit our best physics. This was never supposed to happen. Designed as a 5-year mission to study the giant planets, this spacecraft has been operating for more than 45 years. It left Cape Canaveral in 1977 on a precise trajectory through the solar system, aimed at Jupiter and Saturn, then flung outward by gravity assists. No one expects a 1970s probe with tens of kilobytes of memory and a transmitter weaker than a household light bulb to still be talking from beyond the edge of the sun's magnetic influence. Yet it is. And what it's saying is deeply unsettling. Before we get started, picture what scientists thought the frontier would look like. Beyond the orbit of the outer planets, beyond Pluto, there would be the heliopause, a relatively sharp boundary where the solar wind dies away and true interstellar space begins. Cross that line and the environment should grow quieter. Fewer particles, less structure, long stretches of almost perfect silence. That is not what Voyager 1 found. When it finally crossed the heliopause in 2012, around 121 astronomical units from the Sun, the spacecraft entered interstellar space and kept listening. Its plasma wave instrument, a radio ear tuned to the vibrations of charged gas, began to pick up something unexpected. Not just brief shrieks when solar storms slammed into the boundary, but a constant, faint plasma hum in the dark. A steady tone rising and falling only slowly, as if the interstellar medium itself was singing. Prediction said, quiet. Observation said a background note that never quite goes away. At the same time, the detectors counting energetic particles and cosmic rays started seeing patterns that refused to match the models. Instead of a clean transition from solar particles to galactic ones, Voyager 1 passed through layered, shifting regions. Densities were higher than expected. The magnetic field direction barely changed where it should have rotated. The edge of the solar system was not a neat shell. It was a tangled, compressed, restless boundary. No one predicts a 5-year mission will end up mapping a frontier like this. Absolutely no one anticipates that the further the spacecraft travels into interstellar space, the less sense our equations make. Now, let's begin. By the end of tonight, you're going to understand 7 major discoveries Voyager made as it approached and crossed the heliopause, how it redefined the shape of the heliosphere, revealed a crowded, humming interstellar medium, and exposed contradictions that may point to unknown structures or even new physics lurking just beyond the solar system's fading wind. To understand what Voyager 1 actually discovered, the story has to slow down right at the place everyone once thought would be simple, the edge. For decades, scientists imagined a clean boundary. Inside, the solar wind racing outward from the sun. Outside, the interstellar medium, a thin galactic breeze flowing past. 2 fluids meet, pressure balances, the solar system ends. A neat bubble in space, a line in the equations, a tidy edge to the sun's domain. Reality did not cooperate. Voyager 1 was supposed to pass a termination shock around 75 to 90 astronomical units, then hit the heliopause, the true boundary, around 90 to 100 AU. Designed for a 5-year mission to the giant planets, this spacecraft was never expected to map the frontier. No one expects a 1970s probe with tens of kilobytes of memory to redraw the architecture of the solar system. But the numbers began to drift. The termination shock turned up at about 94 AU, already farther than predicted. The heliopause? Voyager 1 didn't cross it until around 121 AU, more than 2.4 billion miles beyond many early estimates. The bubble was larger, more inflated, and not remotely as spherical as the model suggested. And that was only the first surprise. The heliopause did not look like a crisp wall. As Voyager 1 approached, energetic particles and cosmic rays didn't show one sudden jump. They changed in steps, in layers. Solar particles dropped, then partially recovered, then dropped again. Galactic cosmic rays rose, then plateaued, then surged. It was as if the boundary had multiple skins, each with its own contradictory behavior. Then came the magnetic field. Before we get started on the wilder ideas, consider this. Models said the magnetic field direction inside the heliosphere should differ clearly from the field in interstellar space. A twist, a rotation, a sign the spacecraft had exited the sun's influence. Instead, when Voyager 1 crossed the heliopause in 2012, the field strength jumped, but the direction barely changed. The compass needle turned only slightly when it was supposed to swing. Plasma told a different story. The plasma wave instrument heard the ring of charged particles vibrating around the spacecraft. From that tone, scientists inferred a plasma density several times higher than expected, just beyond the heliopause, as if the interstellar medium there had been compressed and structured by the solar wind's long struggle against it. Then, in 2021, buried in the data, they found something stranger. A persistent, faint plasma hum, a constant background note in interstellar space, not just bursts triggered by solar storms. Tonight, we're going to treat these not as isolated oddities, but as pieces of one larger mystery. 7 major discoveries at the edge of the solar system, unexpected distances, warped shape, layered cosmic rays, stubborn magnetic direction, puzzling density jumps, that eerie plasma hum, and a surprisingly structured interstellar medium, each overturned a different part of the old model. By the end of tonight, you're going to understand how Voyager 1 forced scientists to admit that the edge of the solar system is not a line, but a turbulent, tangled region that our theories barely describe. What exactly is humming out there? Why is the interstellar medium denser and more organized than expected? Are these just aging instruments whispering lies, or hints of new physics, new structures, and perhaps something even stranger, waiting in the dark just beyond the sun's fading wind? Out there, 15 billion miles from your bedroom window, a 1970s spacecraft is hearing a constant, eerie hum in the dark. Not a dramatic sci-fi signal, just a faint, steady vibration in the plasma between the stars that refuses to go away. That quiet sound matters to you more than it seems, because if you are the kind of person who lies awake wondering what's really beyond the planets, this is your frontier. Voyager 1 is not just leaving the solar system, it is dragging human curiosity with it, one data point at a time, into a region no generation before yours could even measure. Tonight, we're going to treat that hum as something personal, a test of how far your species is willing to push to understand the space beyond the sun's fading wind. This strange data is not just a tweak to a textbook diagram. It is a challenge to the entire picture of how stars carve bubbles in the galaxy. The heliosphere was supposed to be a smoother, cleaner boundary, where the solar wind died and the interstellar medium took over. Instead, Voyager 1 crossed a heliopause that was farther out, more compressed, and far more layered than scientists predicted. with cosmic rays and energetic particles changing in sharp, unexpected steps. No one predicts the edge of the system will look like this. Those details matter on Earth. The way the heliosphere interacts with the local interstellar medium helps decide how many high-energy cosmic rays reach your atmosphere and even your electronics. If the plasma out there is denser, more organized, or more turbulent than models suggested, then your solar neighborhood might be less typical than everyone assumed. That affects how we think about other stars, other planetary systems, and how shielded, future interstellar spacecraft, and maybe one day human crews, will be as they push outward. And then there is the pattern interrupt. This is all coming from a probe with tens of kilobytes of memory and a transmitter weaker than a household light bulb. No one expects hardware this old to rewrite modern physics. Absolutely no one anticipates that a faint, persistent tone in interstellar space could force new ideas about magnetic fields, plasma waves, and the true shape of the heliosphere. If deep dives into mysteries like this are your kind of late-night journey, take a second right now to tap like or hit subscribe. It seems small, but it tells the algorithm to show these missions, these questions, to more people who feel the same pull toward the dark beyond the planets. By the end of tonight, you're going to understand what Voyager 1 is really detecting out there and why the answers are so hard to pin down. Every section from here will stay brisk and focused, building piece by piece toward that explanation. No detours, no fluff, just the mission, the measurements, and what they mean. Now, let's begin at the only place this story can start. To understand why the edge of the solar system looks so strange, the timeline has to rewind to 1977, to a Florida launch pad, and to two spacecraft that were never supposed to make it this far. The year is 1977. Heat shimmers above the concrete at Cape Canaveral, and on two separate pads sit two nearly identical machines that will end up rewriting what scientists think the edge of the solar system looks like. Before we get started on the mysteries out beyond the heliopause, the scene here matters. Because at this point, no one expects these spacecraft to escape the sun's influence. The plan is modest: visit a few giant planets, send back pictures, and then fade into the dark. There is Voyager 2 launching first on August 20th, and there is Voyager 1 launching second on September 5th. The numbering looks wrong, it feels backwards, but there is a reason. Voyager 1 is placed on a faster, steeper trajectory that will reach Jupiter and Saturn earlier, crossing key encounter dates first. Mission controllers know that when the world watches the first close flybys, they need the one spacecraft to be the one arriving, to keep operations, news releases, and public understanding aligned, so the name does not follow the launch order, it follows the arrival order, designed for clarity, not ego. Voyager 1 will dive in closer to Jupiter, bend the solar wind of its own path more sharply in Saturn's gravity, and then head upward out of the plane of the planets. Voyager 2 will take the more patient route, opening the door to Uranus and Neptune. Each spacecraft is roughly the size and mass of a small car, but stripped of anything familiar. A 3.7-meter high-gain antenna dish dominates the frame, a white radar-like shield always trying to point back toward Earth. 3 radioisotope thermoelectric generators hang off a boom like metallic fruit, quietly converting the heat of decaying plutonium into a few hundred watts of electrical power. Around the central bus, instruments bristle. magnetometers on long booms to escape magnetic noise, plasma detectors to taste the solar wind, cosmic ray detectors to count high-energy particles, and the famous cameras that will give the planets faces. All of this hardware exists for one reason: a timing trick in the clockwork of the solar system. Once every 176 years or so, the outer planets line up in such a way that a single spacecraft can fall past Jupiter, steal some of its orbital energy, then repeat the maneuver at Saturn, Uranus, and Neptune. This is the Grand Tour concept. Gravity assists act like perfectly placed slingshots, trading the planet's motion for the spacecraft's speed, saving an impossible amount of fuel and decades of travel time. Without that late 1970s alignment, visiting all 4 giant planets with 1970s technology would demand multiple heavy missions, exotic propulsion, or travel times so long that no one predicts political patience would last. The Voyagers are, in a real sense, a bet on celestial mechanics and timing. Tonight, we're going to follow that bet all the way to interstellar space. But first, those gravity-powered flybys will transform what scientists think they know about the outer planets and quietly set up the surprises that appear when the solar wind finally runs out of room. The original plan is simple: 5 years, 2 giant planets, then oblivion. Voyager 1's primary mission is officially just a Jupiter-Saturn tour. The spacecraft will race through the outer solar system, snap tens of thousands of images, map gravity fields, probe magnetic environments, and taste the charged particles riding the solar wind. Then the plutonium in its power source will slowly weaken. Instruments will wink out one by one, and the signal will fade beneath the noise of deep space. No one expects anything else. The hardware is robust, but it is late 1970s robust. 3 onboard computers with memory measured in kilobytes, not gigabytes. A transmitter that radiates about 23 watts, less than a household light bulb. Tape recorders, mechanical relays, and hand-soldered electronics. The design lifetime is 5 years. No one predicts that viewers who are not even born yet will one day watch this mission on high-definition screens and think of that as ancient technology. Engineers know the spacecraft will keep flying. They do not seriously plan for it to keep working. The documents talk about extended missions, but those are modest. Maybe a Saturn encounter for Voyager 1, maybe Uranus and Neptune for Voyager 2 if funding and luck hold. Absolutely no one anticipates that, nearly half a century later, Voyager 1 will still be talking to Earth from beyond the known boundary of the solar system. Now, let's begin to stretch that 5-year clock. Jump forward past the spectacular planetary encounters, past Jupiter's volcanic moon Io and Saturn's rings, revealed as vibrating, wave-shaped systems. The original mission is long over. The spacecraft is billions of miles beyond Saturn, heading up and out of the plane of the planets. Yet in the mid-2020s, there is still a faint, coherent signal returning from the dark. By the end of tonight, you're going to understand just how improbable that is. To keep Voyager 1 alive, engineers have spent decades rationing every watt. They power off heaters, accept freezing instruments, and rewire the mission in software written for 1970s computers. Commands are crafted so that a probe older than many viewers' parents can juggle power loads, wake sensors briefly, then go back into a low-energy trance. And here is the twist. Those brief, carefully planned awakenings after the last planet are when some of the most profound discoveries happen. Once Voyager 1 leaves Saturn behind, it is no longer a planetary tourist. It becomes a scout, driving toward the place where the sun's influence ends and interstellar space begins. For decades, that edge of the solar system is imagined as something near Pluto, a distant ring beyond the last familiar planet. But the real drama is not at Pluto's orbit. It is at an invisible frontier far beyond, where the solar wind slams into the thin gas between the stars. Models predict a clean termination shock around 75 to 90 astronomical units, then a sharp heliopause near 100 AU. Voyager 1 will show that those predictions are wrong, and that the true boundary is stranger, more distant, and far less understood than anyone expected. Those predictions only make sense if you accept one picture of space, a picture drawn in the 1950s, refined in the 60s, and largely locked in by the time Voyager left Earth in 1977. Before we get started with what Voyager actually discovered, you need to see the universe it was launched into on paper. In that universe, the sun is not a quiet light bulb. It is an engine constantly blowing a stream of invisible particles outward in all directions. That stream has a name, the solar wind. The solar wind is not a breeze in air, it is a supersonic plasma, a thin soup of electrons and protons racing away from the sun at hundreds of kilometers per second, carrying the solar magnetic field with it like iron filings frozen into a flowing river. This wind shapes everything. It sculpts planetary magnetospheres, carves comet tails into long glowing streamers, and fills the solar system with charged particles that never truly stop. Tonight, we're going to stand in 1977 for a moment and look out with those assumptions. By the end of tonight, you're going to understand why the surprises at the edge of the solar system were so shocking. In the 1950s, a young theorist named Eugene Parker dared to suggest that this wind had to exist. Using the equations of fluid dynamics and electromagnetism, Parker showed that a hot, ionized corona around the sun could not just sit there. It must expand outward continuously, accelerating until it became supersonic. At the time, many scientists pushed back. Some argued the sun only spat particles during flares. Others insisted a continuous wind would be unstable or impossible. Prediction versus observation settled the argument. Early spacecraft in the 1960s flew through space and directly sampled the plasma. They measured a constant outflow of charged particles day after day, year after year. The solar wind was real, and Parker's once controversial idea became the foundation of heliophysics. The solar system was now seen as a giant bubble blown by this wind into the thin gas between the stars. Quantitatively, that bubble is expensive for the sun. Every second it loses roughly 1 million tons of material in the solar wind. That sounds catastrophic. But compared to the sun's mass, it is negligible even over billions of years. The sun is not evaporating in any practical sense, it is merely shedding a microscopic fraction of itself to inflate a vast magnetic cavity. In the late 1970s, the standard model was elegant. The solar wind races outward supersonically until, far beyond the planets, it slows at a termination shock, then stalls at a relatively clean boundary called the heliopause. Beyond that boundary lies the interstellar medium, extremely tenuous gas and dust, often only about 1 atom per cubic centimetre. Our entire solar system, wrapped in its heliosphere, was thought to move through that medium like a ship through a thin fog. No one expects in that picture that the edge of the bubble will be messy. Voyager will prove that assumption wrong. To understand why Voyager's data is so strange, you first have to understand where it actually is. Not just past Pluto, not just outside the solar system, but inside a layered, invisible structure carved into space by the sun itself. Before we get started, forget the idea of a clean edge. The solar system does not end like a cliff. There is no single line where one side is us and the other side is the galaxy. Instead, there are boundaries, nested, shifting, invisible boundaries where the behavior of the solar wind and the surrounding plasma changes abruptly. Closer in, the solar wind races outward at supersonic speeds, hundreds of kilometers per second, a continuous stream of charged particles launched from the sun. It fills a vast bubble around our system. But that bubble is not expanding into emptiness. It is pushing against the interstellar medium, that thin fog of gas and magnetic field the entire heliosphere is ploughing through. Eventually, the outward wind runs into enough resistance that it can no longer stay supersonic. It slows, it compresses, it heats. That transition happens at a boundary called the termination shock. Think of it as a cosmic sonic boom, a shock front, where the solar wind suddenly drops from supersonic to subsonic as it starts to feel the pressure of interstellar space. Voyager 1 crossed that shock in 2004 at about 94 astronomical units from the Sun, already farther out than most scientists had placed it on their neat diagrams. Beyond the termination shock lies the heliosheath, a turbulent, squeezed-down region of slowed solar wind. Here flows twist, magnetic fields drape and fold, and particles bounce back and forth between inner and outer space. Farther still is the heliopause. This is the outermost major boundary of the heliosphere, where the outward pressure of the sun's plasma finally balances the inward pressure of the interstellar medium. Inside the heliopause, plasma is solar. Outside, plasma is galactic. By the end of tonight, you're going to understand why that simple sentence turned out to be dangerously optimistic. Outside the heliopause, models suggest there might be one more feature, a bow wave, or even a bow shock, ahead of the heliosphere as it moves through the galaxy. If the local interstellar medium is dense and magnetized enough, the heliosphere should create a true shock, like the wave piling up in front of a ship's bow. If it is gentler, the result is only a mild compression. Tonight, we're going to see how even that was up for debate. Now, let's begin to tighten the tension. In the 1990s and early 2000s, the picture seems clear. Termination shock around 75 to 90 AU. Heliopause around 90 to 100 AU. A mostly rounded bubble, maybe with a bow shock ahead. Clean boundaries, predictable behavior. Then Voyager 1 approaches those regions. The termination shock is late. The heliopause is even later, at 121 AU. The transitions are layered, messy, nothing like a single sharp line. The boundary is farther than predicted, the structure is different than predicted, and absolutely no one anticipates what the instruments will report once the spacecraft is finally, officially, in interstellar space. So when Voyager 1 finally steps through that shifting boundary, the question becomes simple and brutal. How do you even know what kind of space you're in when you can't see it? You can't roll down a window. You can't scoop up samples. All you have are a handful of instruments designed in the early 1970s, now trying to make sense of a medium no one has ever visited. Before we get started, imagine this. You're trying to diagnose the weather outside your house, but you're forbidden to look out a window. No images, no direct view of the planets, no view of the solar wind. Only the way the walls vibrate, the way the roof flexes, the faint hiss through tiny cracks. That's Voyager in interstellar space. The most famous ear on the spacecraft is the plasma wave system. Despite the name, it doesn't record sound. There is no microphone riding 15 billion miles from Earth. Instead, This system measures minuscule oscillations in the electric field of the plasma around the spacecraft. Charged particles wiggle. Those wiggles generate waves. The instrument detects their frequency and intensity, and those frequencies can be shifted into the audio range, so scientists can literally listen to the plasma. Now, let's begin with the twist. Voyager 1's original dedicated plasma instrument failed decades ago back in the inner solar system. No one expects that loss to matter much once the planetary tour is over. The mission is supposed to end long before interstellar space becomes relevant. But the spacecraft survives. The plasma instrument does not. So, when it finally crosses the heliopause, the only way to infer the density of the interstellar plasma is through the plasma wave system's music. Higher frequency oscillations mean higher electron density. Lower tones mean thinner gas. By the end of tonight, you're going to understand that those eerie, drawn-out whistles and sudden chirps are not just sound design, they are density measurements. Next, the magnetometer. It rides on a long boom, extended away from the main body of the spacecraft, so that the spacecraft's own magnetic field doesn't drown out the signal. This instrument measures both the strength and the direction of magnetic fields, mapping how the solar field stretches, twists, and finally gives way to the interstellar field beyond the heliopause. When the direction barely changes at the crossing, while density jumps, scientists know the boundary is stranger than every simple model predicted. Then, there are the particle detectors, the cosmic ray subsystem and the low-energy charged particle instruments. These are the counters at the door, logging every high-energy visitor. They distinguish particles from the sun's solar wind from those that come from distant supernovae and galactic accelerators. As Voyager 1 moves outward, the flux of galactic cosmic rays climbs while solar particles drop, revealing how well the heliosphere shields the inner system from harsh radiation, and where that shielding starts to fail. Here's the pattern interrupt. None of this hardware was built to probe the local interstellar medium. The original plan is simple: 5 years, Jupiter and Saturn, then a slow fade into silence. No one predicts that these aging detectors will become humanity's only direct probes of the space beyond the heliopause, yet they are. And the puzzling hums, the mismatched magnetic fields, and the unexpected particle counts they send back are forcing scientists to rethink what the edge of our solar system really looks like, and whether the boundary is a line at all or a tangled, layered region that Voyager 1 is only beginning to sample. Before we get started on the weird hums and impossible readings, there's something important to understand. The surprises at the edge of the solar system only make sense when contrasted with what scientists were absolutely sure they were going to see. For decades, the picture looked clean. The sun blows out a steady solar wind. That wind races outward, thins with distance, and eventually slams into the interstellar medium. In the models, that collision created a neat hierarchy. First, a termination shock somewhere around 75 to 90 astronomical units from the Sun. Then, not much farther out at 90 to 100 AU, the heliopause. A crisp, almost spherical boundary where the solar wind stopped and interstellar space began. The whole heliosphere was drawn like a comet, a rounded nose facing into the galactic headwind, a long tail streaming behind the solar system as it ploughed through space. Elegant, symmetric, predictable. By the end of tonight, you're going to understand why that elegance fell apart. Those early models depended on a stack of assumptions. The local interstellar medium was treated as relatively uniform, a nearly constant density, a smooth flow, no violent clumps or hidden clouds. The local interstellar magnetic field was given a certain strength and direction, strong enough to matter, but not strong enough to dominate. And the solar wind itself was averaged over decades, smoothed into a tidy, long-term, typical behavior that almost no one expects to be dramatically wrong. Now, let's begin following Voyager 1 outward, with those expectations loaded into every prediction. After Jupiter and Saturn, the spacecraft climbed out of the plane of the planets, aimed toward the nose of the heliosphere, past the region of the Kuiper Belt, beyond Pluto's orbit. Through the late 1990s and into the early 2000s, scientists watched the data stream from tens of billions of kilometers away, waiting for the textbook signature of the termination shock. They expected a sudden drop in solar wind speed, a jump in temperature, a change in particle energies that would say clearly, the shock is here. No one predicts that the spacecraft will just keep going and going and going. Voyager 1 blew past 80 AU, then 90. Models were tweaked. Maybe the interstellar pressure is a bit lower, maybe the solar wind is stronger than assumed. The termination shock was pushed outward on paper, but the spacecraft still didn't see a clean crossing. The data showed hints and fluctuations, not the sharp boundary everyone had been promised. By the time Voyager 1 finally crossed the termination shock at about 94 AU in late 2004, the event itself refused to behave. The transition was smeared out, not sharp. The solar wind slowed, but in fits and starts. Energetic particles leaked across the supposed boundary. Absolutely no one anticipates a tidy, one-and-done line. Then, years later, when Voyager 1 stepped through the heliopause around 121 AU, the distances and the behavior of the plasma and magnetic fields delivered a clear message. The edge of the solar system was larger, stranger, and far more layered than any simple comet-shaped bubble. The real mystery was only just beginning. The real mystery was only just beginning. To understand why, you have to rewind a little to the first time Voyager 1 hit one of those outer boundaries and the physics refused to cooperate. Now, let's begin with the termination shock, late 2004. Voyager 1 is about 94 astronomical units from the Sun, roughly 14 billion kilometers out, when its instruments register the crossing. Right away, something is wrong. Models from decades of solar wind theory had placed that shock closer in, nearer 75 to 90 AU. The message is blunt. The heliosphere is either larger, more distorted, or both. Before we get started on what went wrong, remember what scientists thought they would see. The solar wind streams outward at hundreds of kilometers per second, supersonic in this plasma ocean. At the termination shock, it should slam into the interstellar medium and slow abruptly. A sharp drop in speed, a jump in density and temperature. Clear, textbook changes in energetic particle populations as the flow flips from supersonic to subsonic, designed for clarity, a clean line in space. That is the expectation. The reality looks nothing like it. As Voyager 1 approaches 94 AU, its plasma and particle detectors show the solar wind already losing speed. Not in a neat step, but in fits and starts. The flow becomes turbulent, magnetic fields twist, energetic particles leak in strange directions. Instead of a single wall, the spacecraft is flying through an extended region of disturbed plasma. A foreshock, a messy prelude to the main event that no one predicts in such a pronounced form. The termination shock itself, when it finally arrives, is more of a smeared-out transition than a crisp boundary. The speed change is spread over millions of kilometers. Particles are accelerated and scattered in ways that hint at waves and ripples riding on top of the shock. The solar wind does slow and heat up, but the script is wrong. The edge of the solar system is not behaving like a simple bow wave. Then comes the second act. In 2007, Voyager 2 crosses the termination shock as well, but at a different latitude and at a different distance, around 84 AU. Same star, same solar cycle, just shifted. Different shock location. The implication is unavoidable. This is not a smooth sphere around the Sun. It is a distorted, possibly wavy surface, pushed in on one side by the local interstellar medium, and breathing in and out with the solar cycle. Tonight, we're going to use that distortion as a clue. By the end of tonight, you're going to understand why a dynamic, rippling termination shock makes the outer heliosphere almost impossible to predict, and why, beyond it, Voyager 1 begins to detect things that absolutely no one anticipates. That rippling termination shock is only the beginning. Beyond it, Voyager 1 enters a region where the most dangerous radiation in space is waiting: galactic cosmic rays. These are not gentle particles. They are protons and atomic nuclei hurled across the galaxy by supernova explosions, shock fronts, and other extreme events. Moving at relativistic speeds, they can slice through electronics, damage DNA, and over long timescales they quietly shape the habitability of planets. The entire solar system lives inside the Sun's partial shield against them, the heliosphere. Before we get started on what Voyager actually saw, it helps to understand the expectation. As the spacecraft pushed outward, scientists predicted a simple pattern. The farther you get from the Sun, the weaker the solar wind's magnetic protection. The weaker that protection, the more galactic cosmic rays should seep in. So as Voyager 1 approached the heliopause, the cosmic ray intensity should rise smoothly, like walking from the shade into sunlight. That is not what happened. In 2012, around 120 astronomical units from the Sun, the detectors on Voyager 1 recorded sharp, step-like jumps in cosmic rays, not over tens of astronomical units, over distances comparable to the scale of the solar system's planets. In some steps, high-energy galactic cosmic rays surged upward. At the same time, lower-energy particles tied to the inner heliosphere dropped. Expectation, a gradual ramp; reality, a staircase. No one expects a clean boundary to fracture into multiple, nested layers. Yet that is what the data demanded. One moment, Voyager is in a region where heliospheric particles dominate. A short time later, those particles plummet while galactic cosmic rays spike. Then, a little farther on, the pattern shifts again. It is as if the spacecraft is crossing a series of invisible shells, each with a different mix of particles and magnetic connections. Then the pattern interrupt arrives, the dropouts and spikes. Just before the heliopause crossing, Voyager 1 sees sudden disappearances of heliospheric energetic particles, followed by abrupt returns. Galactic cosmic rays show complementary spikes. By the end of tonight, you're going to understand why those flickers are so unsettling. The leading interpretation is that Voyager is drifting through magnetic structures, flux tubes, that alternately connect it back to the inner solar system or out to interstellar space. When the field lines thread inward, heliospheric particles can stream along them. When they connect outward, galactic cosmic rays flood in instead. The boundary is not a line, it is a tangled web. Now, let's begin to reframe the edge of the solar system. It does not act like a solid wall blocking radiation. It behaves like a leaky, semi-permeable membrane, where the Sun's magnetic field is shredded, folded, and intermixed with the interstellar field, creating preferred pathways for cosmic rays to sneak through. For deep space missions, this changes the stakes. Radiation exposure beyond the planets will not be a simple function of distance. It will depend on where these magnetic corridors open and close, something that so far absolutely no one anticipates with confidence. And if the particle boundary is this tangled, what does that say about the magnetic field itself on the other side of the heliopause? So, when the particle boundary looks like a maze, the next question is obvious. What happens when the spacecraft finally hits the wall itself? August 2012. Voyager 1 is nearly 18 billion kilometers from the Sun, about 121 astronomical units out, riding through space where sunlight is weaker than a distant star. Then, over just a few days, its particle detectors see something dramatic. The flux of lower energy particles from the solar wind plunges. At the same time, higher energy galactic cosmic rays surge to record levels. Designed for a 5-year mission to study 2 planets, this spacecraft now seems to be tasting the galaxy beyond. On paper, that looks like a clean crossing. Inside the heliosphere, the solar wind dominates. Outside, interstellar space does. So when solar origin particles disappear and galactic cosmic rays jump, the obvious headline is, Voyager 1 has left the solar system. But scientists hesitate, because one instrument refuses to cooperate with the story. Models say that at the heliopause, the magnetic field direction should change significantly. Inside, field lines are dragged out by the rotating sun. Outside, they're anchored in the local interstellar medium. Prediction versus observation could not be clearer. Yet Voyager's magnetometer reports something strange. The magnetic field strength increases sharply as if the spacecraft is pressing into denser, more compressed plasma. But the direction? It barely rotates at all. No one expects that. The boundary was supposed to be sharp, obvious, textbook. Instead, the data look like a contradiction written in magnetic ink. So the community splits. One camp argues that Voyager has entered a new region inside the heliosphere, a helios sheath depletion region, where the solar wind is drained of energetic particles but the field lines are still solar. Another camp says the spacecraft really is in interstellar space, and that by cosmic coincidence the interstellar magnetic field happens to line up with the solar one right where Voyager crosses. For months, papers, conferences, and late-night calls orbit a single question: where is this spacecraft, really? The particle data scream outside. The magnetic data whisper, not yet. By the end of tonight, you're going to understand why that tension mattered so much for every model of the solar system's edge. The tiebreaker comes from a quieter instrument. Voyager 1's plasma wave detector cannot measure bulk flow directly, but it can hear the density. In 2013 and 2014, a powerful solar storm sends a shock wave racing outward through the solar wind. When that shock reaches Voyager, it rattles the surrounding plasma and sets it ringing like a bell. Those oscillations reveal a crucial number. The ambient electron density is far higher than in the heliosheath and matches expectations for the local interstellar medium. The spacecraft is no longer in the sun's wind, it is in the galaxy's. By late 2013, consensus hardens. Voyager 1 crossed the heliopause in August 2012, entering interstellar space. But the boundary it passed was layered, asymmetric, magnetically confusing, a frontier no one predicts in detail. Now, let's begin to ask what that strange crossing implies for everything Voyager 1 detects deeper in the dark. The plasma said, "You're out." The particles said, "You're out." But when Voyager 1 checked the magnetic field beyond the heliopause, something refused to line up with the script. Before we get started on why that matters, remember what scientists expected at this boundary. Inside the heliosphere, the Sun's magnetic field is carried outward by the solar wind, spiraling like a giant, rotating lawn sprinkler. Far beyond, the galaxy has its own magnetic field frozen into the interstellar medium. The models said these two regimes should meet at a clear angle, like two different roads crossing at a junction. So the prediction is simple. Cross the heliopause and the magnetic field direction should pivot, not a tiny nudge. A noticeable turn, designed for a 5-year mission to the outer planets. This spacecraft is now 120 astronomical units out, about 18 billion kilometers from the Sun, giving humanity its first direct chance to measure that turn. What Voyager 1 actually detected is stranger. As it passed into the region where the solar wind drops away and interstellar plasma dominates, the strength of the magnetic field jumped. That makes sense. A denser medium can support a stronger field, but the direction of that field, it barely budged. The orientation changed only modestly, staying within about 20 degrees of the heliospheric field direction. Expectation versus reality, again. The boundary was layered instead of sharp. The density was higher than predicted, and now the magnetic field direction looks almost familiar. No one expects the interstellar field to politely line up with the Sun's like two compasses in formation. No one predicts such a small directional shift at the very point where one domain is supposed to give way to another. So what does this mean? Either humanity is incredibly lucky, and the local interstellar magnetic field just happens to be nearly aligned with the heliospheric field in this part of space. Or the heliosphere is doing something far more complex than the early diagrams implied. By the end of tonight, you're going to understand why that second option has become so compelling. One leading idea is magnetic draping. As the solar system plows through the galaxy, the interstellar field lines might wrap around the heliosphere's nose, stretched and twisted by the Sun's motion and the pressure of the solar wind. In that picture, by the time those external lines reach the region where Voyager 1 exited, they have already been bent into rough alignment with the heliospheric field. Another proposal says Voyager 1 may still be in a transitional zone, a magnetic highway where field lines from inside and outside connect, allowing particles to stream freely while the direction remains blended. In that case, the spacecraft is beyond the solar wind, yet not fully immersed in undisturbed interstellar space. Now, let's begin to see the real problem. A decade after the crossing, the magnetic data at and just beyond the heliopause remain one of the central reasons scientists say Voyager 1 is detecting things in interstellar space that cannot be fully explained. If even the magnetic compass of the galaxy is ambiguous here, what does that imply about the waves, the hum, and the invisible structures waiting deeper in the dark? If the magnetic compass is confused, the next question is obvious. What about the air of interstellar space itself? Not oxygen and nitrogen, but the thin plasma that fills the galaxy. When Voyager 1 crossed the heliopause, scientists expected a gentle step into that medium. Instead, the spacecraft heard something denser, tighter, more compressed than the models allowed. Now, let's begin with how a 1970s spacecraft measures something it cannot touch. Voyager 1 carries a plasma wave instrument. It does not count particles directly. It listens. When charged particles in space are disturbed, they ring like a bell at a frequency set by the electron density. Higher density, higher pitch. By measuring that pitch, scientists can calculate how many electrons occupy each cubic centimetre around the spacecraft. For years beyond Saturn, the solar wind was too tenuous and too cold for that bell to ring reliably. Then the heliopause crossing in 2012 changed everything. Solar eruptions sent shocks racing outward, ploughing into the interstellar medium beyond the boundary. Each shock made the local plasma oscillate. Voyager's instrument recorded the tone. From those tones, researchers inferred densities of around 0.08 electrons per cubic centimetre just outside the heliopause. On paper, that number looks tiny, less than 1/10 of an electron per sugar cube volume of space. But prediction versus observation matters. Before Voyager, some models of the local interstellar medium suggested densities closer to 0.002 to 0.01 electrons per cubic centimetre. The reality was up to an order of magnitude higher. No one expects a region that empty to come in too dense. No one predicts a vacuum that surprises the calculators. The implication is dramatic. A denser interstellar medium means the galaxy is pressing harder on our solar system than scientists thought. The heliosphere is not an overinflated balloon drifting in a near-perfect void. It is a bubble squeezed from outside by the weight of the local cloud, by large-scale galactic magnetic fields, and by the ram pressure of our motion through space. A stronger external squeeze forces a smaller, more confined solar bubble. That changes more than just a diagram in a textbook. A tighter heliosphere alters how cosmic rays are filtered before they reach the planets. It reshapes the heliosphere's tail, possibly stretching it into a distorted, comet-like structure instead of a neat, symmetric shell. By the end of tonight, you're going to understand that every one of those details feeds into how habitable space is carved out around our star. Then comes the pattern interrupt. The density does not stay put. After the initial measurements, Voyager 1 kept listening. Between shocks, it detected a faint, continuous plasma hum, and over the years that hum crept to higher frequencies. The inferred density gradually rose beyond 0.1 electrons per cubic centimetre, hinting at layers, ripples, and gradients in the interstellar medium. So, the space beyond the heliopause is not uniform. It is structured, clumpy, possibly corrugated by passing shocks and tangled magnetic fields. Absolutely no one anticipates that a region once drawn as an empty, featureless background would reveal this much texture, and as Voyager 1 pushes farther, each new change in that invisible pressure will test the next idea about what truly lies beyond the solar wind's fading reach. That invisible pressure is one surprise. But in 2021, scientists realized Voyager 1 had been hearing something even stranger the whole time it was out there. Not a sharp crack from a passing shock, a background note, a quiet, eerie hum that seems to fill interstellar space itself. Now, let's begin with what everyone expected. For years beyond the heliopause, Voyager's plasma wave instrument behaved just as the model said it should. Most of the time, it heard almost nothing. Then, when a powerful solar storm blasted outward, months or even years later, a shock wave would finally reach Voyager, compress the local plasma, and ring it like a bell. Brief bursts of oscillations, short, bright tones in an otherwise silent void. Those tones were already useful. Their frequency reveals the local electron density, so each burst gave a snapshot of how compressed the interstellar medium was at that moment. But between bursts, the instrument looked nearly flat, quiet, empty. That matched the picture of interstellar space as a cold, mostly inactive plasma, disturbed only when the solar wind or a rare supernova shock happened to pass by. Then a team went back to the data with a different question. What if there was something hiding between the bursts? In 2021, they filtered, stacked, and stretched years of measurements looking beyond the obvious spikes. And there it was, a faint, persistent signal. A nearly continuous plasma oscillation at a specific frequency, drifting only slowly over time. Not a random hiss, a steady tone indicating a stable background density in the interstellar medium all around the spacecraft. No one predicts that interstellar space will sing quietly all the time. The expectation was simple: plasma waves mainly excited by transient events, long periods of silence in between. Instead, Voyager 1 reports a constant, low-level hum, as if the local plasma is never truly at rest. That hum has been detectable for years, lurking under the louder solar-driven shocks. So, where does this interstellar song come from? One possibility is small-scale turbulence. Countless tiny eddies in the magnetic field and plasma, each too weak to notice alone, but together sustaining a background vibration. Another is the influence of distant shock fronts, supernova remnants or old solar eruptions whose energy diffuses through the medium and keeps it gently stirred. Or it might be subtle instabilities in the interstellar plasma itself, processes that current models do not yet fully understand or include. By the end of tonight, you're going to understand why this is more than a curiosity. A persistent hum means there is interstellar weather. Slow, continuous, structured. The local medium is not just a static backdrop beyond the solar system's boundary. It has pressure gradients, waves, and long-lived motions. Absolutely no one anticipates that a 1970s spacecraft will become the first observatory of this quiet storm. And the mystery deepens, because as that background tone slowly shifts in frequency, it hints that Voyager 1 is moving through regions with changing density, subtle currents and clouds that models struggle to reproduce in detail. If the hum is the song of interstellar space, the next question is simple and unsettling. What, exactly, is conducting the orchestra? Incredibly, the answer comes from listening not just to the note, but to how that note wobbles. By tracking tiny changes in the plasma wave frequencies and intensities over months and years, scientists can do more than measure an average density. They can watch that density flicker, rise, fall, ripple. Those fluctuations are the fingerprints of turbulence of waves passing through the interstellar medium just beyond our solar system's boundary. Now, let's begin to treat this region the way a meteorologist treats Earth's atmosphere. Voyager 1's plasma wave instrument keeps hearing the tone shift by a few hertz here, a few hertz there. The volume swells slightly, then fades. Over a few months, the inferred electron density steps upward. A year later, it dips. The spacecraft is not in a uniform void. It is moving through patches, regions of slightly different pressure, temperature, and magnetic structure like slow-motion fronts in space. The pattern is unmistakable. Instead of a smooth, steady medium, the data show that interstellar space near the heliopause is mottled. One interval suggests a denser, compressed pocket, perhaps squeezed by a distant supernova shock that has taken hundreds of thousands of years to arrive. Another interval looks calmer, with weaker wave activity, as if Voyager has slipped into a rarefied eddy downstream of some galactic obstacle. No one expects such rich structure on these scales, yet the spacecraft keeps reporting it. This is where the phrase interstellar weather becomes more than a metaphor. Just as Earth's atmosphere has jet streams, cyclones, and clear skies, the plasma between stars appears to have its own dynamic patterns, driven by supernova explosions, stellar winds from massive stars, and the vast magnetic fields threading the Milky Way. The timescales are enormous, the motions slow, but the physics is familiar. Pressure gradients, waves, shocks, and turbulence shaping a medium that never truly rests. By the end of tonight, you're going to understand why this matters for the solar system itself. Turbulence in the local interstellar medium can twist and tangle magnetic field lines at the heliopause, changing how and where magnetic reconnection occurs. That, in turn, alters how galactic cosmic rays penetrate the boundary, which particles are deflected, and which reach the planets, and ultimately, you. The very shape and stability of the heliosphere's outer layers depend on this unseen, shifting weather beyond. But here is the frustrating part. Our models of the local interstellar medium are still coarse, like global weather maps with only a handful of data points. Voyager 1 is just one spacecraft, on one trajectory, sampling a single thin line through a three-dimensional storm. No one predicts that such sparse measurements would reveal this much complexity, and absolutely no one anticipates how many new questions they would raise. If this is what one line looks like, what hidden structures are waiting just a few degrees away in the dark? So scientists zoom out from that single thin line and ask a bigger question. What if the heliopause isn't a wall at all? What if the edge of the solar system is built like an onion with layers upon layers that Voyager's instruments are only just beginning to resolve? Now, let's begin. Near the heliopause, Voyager 1 doesn't see one clean jump from solar to interstellar. It records step-like changes in cosmic rays. Galactic particles surge upward in sudden plateaus, while solar energetic particles drop in matching stair-steps. At the same time, the plasma wave instrument hears the local electron density rising, not in a single spike, but in a series of structured increases spread over tens of millions of kilometers. And through all of this, the magnetic field direction barely twists, staying unexpectedly aligned with the solar field. That combination should not exist in a simple model, designed for a sharp boundary where solar wind stops and interstellar plasma begins. The old diagrams predict a clear before and after. The reality is a stack of overlapping regions. First, an inner heliosheath, where the solar wind has slowed, heated, and become turbulent. Then, just beyond, a depletion region where solar particles almost vanish, yet the magnetic field still looks like it belongs to the heliosphere. Farther out, densities match the interstellar medium, but the field strength and direction are still transitioning, as if the spacecraft is moving through a blended zone rather than a border. Tonight, we're going to treat that blended zone not as an error, but as a clue. One leading idea is that magnetic reconnection at the boundary creates islands or flux ropes, twisted bundles of magnetic field lines that pinch off and roll like cosmic smoke rings. Inside these islands, field lines from the solar wind and the interstellar medium are spliced together, opening localized channels where particles can leak across the boundary in both directions. Pattern interrupt. This means the heliopause may function less like a skin and more like a porous reef. Voyager's step-like cosmic ray changes could be the spacecraft drifting from one magnetic island to another, each with its own mix of solar and galactic particles. The gradual, layered density increases would then mark regions where interstellar plasma has seeped in and been compressed, rather than a single shock front. Voyager 2 drives this home. It exits the heliosphere at a different latitude, at a different distance, and during a different phase of the solar cycle, and its particle and field data show a boundary that is similar in concept, but not in detail. No one expects identical crossings. No one predicts that solar maximum versus solar minimum, combined with the direction of the interstellar magnetic field, would sculpt the interface into a lopsided, ever-shifting shape. By the end of tonight, you're going to understand the key lesson. The edge of the solar system is not a line you cross once. It is a tangled, layered region where winds, fields, and particles from a star and its galaxy wrestle for control. And Voyager has only sampled 2 narrow exit wounds in a 3-dimensional living boundary that every star must carve into the space around it. So now the question becomes uncomfortable. Out of everything Voyager 1 has reported from beyond the heliopause, what is actually mysterious, and what just looked strange because expectations were wrong? Before we get started, it helps to clear away the early ghosts. Some of the first impossible results are now almost routine in heliophysics. The heliosphere turned out to be larger than predicted, stretched and squashed by the galactic wind and nearby interstellar clouds. The heliopause, once imagined as a clean, sharp shell, is now accepted as a structured, dynamic boundary, rippling as the solar wind pressure rises and falls over the 11-year cycle. Prediction versus observation played out over and over. Models favored a mostly spherical bubble. Voyager 1 and 2 discovered an asymmetric, dented shape. Many scientists expected a single abrupt step in particle fluxes. The spacecraft measured layered ramps and temporary leaks where solar particles sneaked far beyond the supposed edge. Those are no longer unexplained. They're the new normal picture of how a star carves out its cavity in galactic space. What remains stubborn are the anomalies that survived a decade of reanalysis. The most famous is the magnetic field direction. Crossing from the solar wind into the interstellar medium, Voyager 1 saw the field strength jump, as expected, but the direction rotated only modestly. Inside and outside the heliopause, the field lines seem almost aligned, as if the galaxy's magnetism and the solar system's internal field had quietly agreed to point the same way. No one predicts that. Geometry can explain some of it, but not all. Then there is the plasma hum. In 2021, scientists realized that beneath the sharp ringing triggered by individual solar shocks, Voyager's plasma wave instrument is hearing a constant, faint tone from the interstellar medium. A steady oscillation in electron density, persisting for years, in a region that was expected to be quiet except during storms. Is it a long-lived wake from past solar events, a signature of large-scale interstellar turbulence, or something about the local galactic environment that models missed? Layered particle transitions are another live puzzle. Instead of a single clean switch from solar particles to galactic cosmic rays, Voyager 1 saw multiple, staircase-like drops and rises, with narrow regions where intensities changed dramatically over distances smaller than Earth's orbit. That implies thin sheets, folds, or magnetic islands at the boundary, but their exact structure is still debated. Part of the difficulty is that this mission is flying half-blind. The prime plasma instrument on Voyager 1 failed long before the heliopause crossing. To estimate plasma density, scientists listen to wave frequencies and watch how the spacecraft charges and discharges. Aging electronics, drifting baselines, and painfully slow telemetry mean that every conclusion is an inference stacked on top of another inference. So competing explanations coexist. Some researchers argue that complex but conventional plasma physics, magnetic reconnection, turbulence, and draped interstellar fields can produce aligned directions, layered transitions, and a persistent hum. Others suspect that Voyager has wandered into a previously unmodelled interstellar structure, perhaps a nearby cloud boundary, a large-scale fold in the galactic magnetic field, or a compressed region shaped by ancient supernova shocks. No one expects exotic new forces here, but absolutely no one anticipates how weird ordinary plasma can be when stretched across tens of billions of miles. Now, let's begin the next step. To understand why these puzzles are so hard to kill, the data from a single aging spacecraft is not enough. By the end of tonight, you're going to understand how Voyager's strange readings compare with other missions, with energetic neutral atom maps, and with our broader picture of where the solar system sits inside the galaxy, and whether these unexplained signals really point to something fundamentally new about interstellar space. But there's an uncomfortable possibility hiding underneath all of this. What if the weirdest thing in interstellar space is Voyager 1 itself? The instinct is to blame the medium, strange plasma density, twisted magnetic field lines, cosmic rays doing things no one predicts. Yet this spacecraft is nearly 50 years old, running on a power source that has been fading since the late 1970s, with electronics that predate the first home computers. Before we get started on exotic new physics, there's a hard question to ask. How much of the mystery lives inside Voyager's own circuits? Think about what this mission has survived. Decades in deep space bathing in high-energy cosmic rays that can flip bits and slowly damage components. Extreme cold, where the bus sits only a few degrees above the background of space. Power levels that keep dropping, forcing engineers to switch heaters off, reroute power, and wake instruments in carefully timed sequences. Each of those choices changes temperatures, voltages, and noise. And that, in turn, can nudge sensor calibration, shift baselines, and make random electronic hiss look a little more like a signal. Tonight, we're going to focus on one crucial example. Voyager 1's primary plasma instrument, the plasma science experiment that was supposed to directly measure the flow of the solar wind and the interstellar plasma, failed years before the heliopause crossing. When the spacecraft finally stepped beyond the solar wind's boundary in 2012, that sensor was silent, so scientists had to improvise. They turned to the plasma wave instrument, which does not measure density directly. Instead, it listens for natural radio emissions in the plasma and uses their frequency to infer density through a model of how charged particles oscillate. That's elegant, it's also indirect. To get from a faint tone in the radio band to 0.13 electrons per cubic centimeter, scientists must assume the waves they are hearing really are plasma oscillations, that the local magnetic field behaves within a known range, and that the spacecraft's own electronics are not contaminating the signal. No one expects a 1970s tape recorder and analog front end to behave perfectly after decades in interstellar space. Absolutely no one anticipates that every component will still match its original calibration chart. So how do they check? They cross-examine Voyager 1's story against other witnesses. Voyager 2 crossed the heliopause at a different point in the solar system, at a different time in the solar cycle, with its plasma instrument still working. Its direct density readings and its own plasma wave tones both show the same pattern, a compressed, denser interstellar medium just beyond the boundary. Remote missions like IBEX map energetic neutral atoms streaming back toward the inner planets and independently reveal a structured, asymmetric heliosphere. New Horizons, much closer in, measures the fading solar wind and provides upstream conditions the Voyagers should encounter later. When these independent lines converge, direct plasma data from Voyager 2, wave-derived densities from Voyager 1, energetic atom maps from IBEX, cosmic ray spectra from both spacecraft, and broader astrophysical constraints from pulsar dispersion and starlight absorption, the anomalies do not vanish. They sharpen. The high densities just beyond the heliopause, the layered transitions in cosmic rays, the oddly oriented magnetic field, they all remain. Now, let's begin to treat Voyager's quirks as part of the signal, not the whole explanation. Instrument aging is real, calibration drift is real, but the agreement across multiple spacecraft methods and wavelengths suggests that most of these unexplained features are telling us something true about the environment beyond the solar wind's reach, not just about a tired spacecraft. The next step is to ask what kind of interstellar neighborhood could force every one of these independent measurements to line up in the same strange direction. So if every independent measurement is pointing in the same strange direction, what is that direction? To answer that, you have to zoom out from a single point in space and look at the whole sky at once. Voyager is like a probe dropped into the ocean. It can tell you the temperature and currents right where it is. But to understand the shape of the coastline, scientists need something else. Tonight, we're going to follow a different mission that stayed deep inside the solar system, pointed its cameras outward, and discovered that the edge of our solar wind is wrapped in a feature absolutely no one anticipates. That mission is NASA's Interstellar Boundary Explorer, or IBEX. Instead of flying to the boundary, IBEX orbits Earth and watches for energetic neutral atoms, or ENAs, that come flying in from far beyond the planets. These ENAs are born when charged particles from the solar wind or the interstellar medium steal or lose electrons during collisions. Once neutral, they stop following magnetic field lines and shoot off in straight lines. By counting where they arrive from, IBEX turns the whole sky into a map of the invisible frontier. When those first all-sky maps came back, the expectation was simple: a smooth glow, maybe brighter, in the direction where the interstellar wind slams into the heliosphere. Instead, there was a narrow, bright band arcing across the sky, a ribbon of enhanced ENA emissions that no model predicted. Crossing that ribbon, an even broader belt appeared. Together, they encircled the sky like a cosmic scar. The most unsettling part was the alignment. That ribbon isn't random. Its orientation lines up with the local interstellar magnetic field, the large-scale field threading the space between stars. That told scientists the heliosphere's boundary isn't just a pressure bubble. It is interacting with an ordered magnetic environment that seems to carve out preferred directions where particles can leak in and out. Voyager cannot see the ribbon directly. Its detectors are tasting the plasma and magnetic field at a single moving point, not imaging the whole sky. But those point measurements are gold. The magnetic field strength and direction Voyager records just beyond the heliopause, the unexpected plasma densities, the way energetic particles rise and fall in layers, all of that feeds into models that try to explain where, along the boundary, those ENAs are being launched. By the end of tonight, you're going to understand that this isn't a smooth, symmetric bubble. The ribbon implies that the heliosphere is draped by the interstellar magnetic field with folds, wrinkles, and corridors where particle exchange is favored. No one expects such strong anisotropy. No one predicts such a clean global signature. Put together, IBEX's all-sky ENA maps and Voyager's local measurements reveal a hidden magnetic skeleton, a framework shaping the space just beyond the solar wind's reach. But if that skeleton is real, the next mystery is even deeper. What exactly is it doing to the interstellar medium Voyager is now entering? That hidden magnetic skeleton is the backdrop. But to see what it actually does to real plasma and particles, you need more than one probe. Tonight, we're going to put Voyager 1 side by side with its twin and watch the edge of the solar system change shape, depending on how you leave it. Now, let's begin. Voyager 1 and Voyager 2 start as near clones. Same launch year, same basic spacecraft, same original mission. Then their paths diverge. Voyager 1 swings past Jupiter and Saturn and then turns sharply north, out of the plane where most planets orbit, trading future encounters for a faster escape into deep space. Voyager 2 takes the scenic route, bending southward to hit all 4 giant planets, arriving at Uranus in 1986 and Neptune in 1989 before angling down toward the southern flank of the heliosphere. That choice of trajectories matters. Voyager 1 barrels outward and crosses the termination shock in 2004, then the heliopause in 2012, at a relatively high northern latitude and during a different phase of the solar cycle. Voyager 2 lags behind, but it carries something Voyager 1 has already lost, a working plasma instrument. When Voyager 2 meets the termination shock in 2007 and the heliopause in 2018, it can directly measure the solar wind's speed, density, and temperature as the spacecraft punches through the boundary. Prediction versus observation comes into sharp focus here. Models once drew a nearly spherical heliosphere with the termination shock at roughly the same distance in every direction. Reality refuses. Voyager 1 hits the termination shock at about 94 astronomical units. Voyager 2 finds it closer in, near 84 AU. Years later, Voyager 1 reaches the heliopause at about 121 AU. Voyager 2 crosses at roughly 119 AU, 2 exits, 2 distances. The only way to reconcile them is to accept a squashed, asymmetric heliosphere, squeezed and distorted by the interstellar magnetic field and the properties of the local cloud flowing past the solar system. The plasma data sharpen that picture. As Voyager 2 moves outward, its instrument watches the solar wind slow, heat, and then collapse towards zero at the heliopause. Beyond, it detects denser, cooler interstellar plasma pressing in. Voyager 1 has to infer this from plasma waves instead of bulk flow, but both spacecraft agree on the broad strokes. Sharp drops in solar particles, abrupt rises in galactic cosmic rays, and a magnetic field that rotates but does not flip in the way many scientists expected, yet the details refuse to line up cleanly. Voyager 1 sees layered, step-like changes in particle flux. Voyager 2 sees smoother, but still structured, transitions. Turbulent signatures differ. The thickness of the boundary region is not the same. No one predicts such a patchy, time-variable frontier where the heliopause can look like a crisp surface in one direction and a ragged, foamy zone in another. By the end of tonight, you're going to understand why that's so unsettling, because even with 2 exits, these spacecraft are sampling 2 narrow needles in a vast, multi-dimensional haystack. The global architecture of the heliosphere, its true shape, its tail, its ripples, remains mostly uncharted. And as Voyager 1 pushes farther into interstellar space, the next puzzle emerges. Do the strange signals it now detects reflect that distorted boundary behind it, or something far stranger ahead? To understand that something far stranger ahead, you have to zoom out from the spacecraft and look at the ocean it's sailing through. Our solar system is not drifting through empty space, it's ploughing through a vast, invisible mist called the local interstellar cloud. Before we get started, picture this cloud not as a dense fog, but as an almost perfect vacuum that still has just enough gas, dust, and magnetic field to push back against the solar wind. Tonight, we're going to treat it as Voyager's new environment, its new laboratory, and see how that environment quietly shapes every measurement the mission sends home. The local interstellar cloud is relatively warm and partially ionized. Temperatures hover around 7,000 Kelvin, hotter than the surface of some cooler stars, yet spread over such low densities that it feels effectively cold. There are only about 0.2 atoms per cubic centimetre. Compare that to Earth's atmosphere at sea level, around 10 to the 19th atoms in the same volume. Interstellar space is an unimaginably better vacuum than any chamber scientists can build, but it is not nothing. Those few atoms and electrons carry pressure, they carry momentum, and they sit in a magnetic field of a few microgauss, a field so weak no one expects it to matter in daily life, but over light years it becomes a sculptor, carving the boundary around our solar system. Here is the key. The size and shape of the heliosphere depend sensitively on these properties. A denser or higher pressure cloud squeezes the solar wind bubble, pushing the heliopause inward. A more tenuous region lets it swell outward, like a balloon drifting into thinner air. Models once imagined a smooth, almost spherical bubble. Voyager 1 and 2 discovered something more distorted, more asymmetric, hinting that the local interstellar cloud is not uniform at all. By the end of tonight, you're going to understand why Voyager's weird data is priceless. For decades, the local interstellar cloud was known only through indirect clues. Stellar absorption lines, tiny fingerprints in the light from nearby stars, and radio observations that suggested temperature, density, and magnetic field. Good estimates, but not ground truth. Voyager changes that. Its plasma wave instrument measures the local electron density directly, using the natural ringing of the plasma around it. Its magnetometer feels the direction and strength of the interstellar field. When those readings show higher than expected densities and subtle twists in field direction, they don't just challenge heliosphere models, they recalibrate the properties of the entire local cloud. Now, let's begin to think on longer timescales. The Sun is not anchored. It orbits the galactic center, carrying the planets and the heliosphere through a patchwork of different clouds and interstellar environments over millions of years. No one predicts that the local interstellar cloud is the only such region. As the Sun drifts into denser clouds, the heliosphere would shrink, cosmic rays would penetrate more easily, and Earth's radiation environment could subtly shift. In more rarefied zones, the bubble would expand, strengthening our shield. Voyager's measurements are the first direct sample of one phase in that journey. The next mystery is whether the unexplained signals it now detects are simply local quirks of this cloud, or early hints of the next region the solar system is about to enter. So, if Voyager's strange signals might hint at the next cloud the solar system is about to enter, the obvious question is, what should the magnetic field out there look like in the first place? To answer that, scientists had to start far beyond the edge of the heliosphere, with beacons scattered across the galaxy. Before we get started with Voyager's local puzzle, Step back to the 1960s and 70s. Long before any spacecraft could dream of reaching the heliopause, astronomers were already probing interstellar space using distant radio sources, pulsars, quasars, and radio galaxies. Their signals cross thousands of light-years of tenuous plasma. Along the way, the interstellar medium leaves fingerprints on that radiation. One of those fingerprints is dispersion. Lower frequency radio waves travel slightly more slowly through ionized gas than higher frequency waves. When a pulsar flashes, the pulse arrives smeared out in time, with high frequencies first and low frequencies last. Measure that delay, and you measure how many free electrons sit between here and there. Over dozens, then hundreds of pulsars, scientists mapped the large-scale electron content of the galaxy. The second fingerprint is even more important for Voyager's story: Faraday rotation. As polarized radio waves move through a magnetized plasma, the plane of polarization slowly twists. The amount of twist depends on both the density of electrons and the strength and direction of the magnetic field along the line of sight. By comparing dispersion and rotation together, astronomers pulled out an average magnetic field, a few microgauss, threading the Milky Way like invisible rails. Tonight, we're going to connect those distant rails to the tiny region Voyager now samples. Those pulsar and quasar measurements do not just give a strength, they give a direction. They suggest that, in our part of the galaxy, the large-scale interstellar magnetic field runs at a particular angle relative to the galactic plane and relative to the direction the Sun is ploughing through the space. That orientation fed directly into heliosphere models. If the solar wind blows outward, while the interstellar field comes in skewed, the heliosphere should be squashed on one side, elongated on another, and the magnetic field outside should drape around the heliopause in a predictable way. By the end of tonight, you're going to understand why no one expects that drape to ignore millions of light-years of ordered field, and absolutely no one anticipates it to flip direction right at our doorstep. Yet that is close to what Voyager appears to see. Just outside the heliopause, the magnetic field direction measured by the spacecraft is not cleanly aligned with some of those broader expectations. The strength jumps, the direction shifts only modestly, and the local orientation seems stubbornly close to the inner heliospheric field. So which is wrong? The distant pulsars or the local probe? Probably neither. The tension suggests that the path from galactic scale averages to local conditions is far more twisted than the simple models implied. Turbulence, folds, and compressed layers near the boundary could distort the field on scales of a few astronomical units, even while the long-range average still follows the pulsar-inferred pattern. Reconciling those scales from pulsars thousands of light-years away to a spacecraft barely 20 light-hours beyond the solar wind's last stand is now one of the central challenges. And the real twist is that Voyager's most puzzling signals may not come from the field direction at all, but from something even stranger, hiding in the plasma itself. So what is hiding in that plasma? Not a dramatic explosion, not a sharp crackle, but a steady, eerie tone. After each solar storm fades, Voyager 1 keeps hearing a quiet, persistent hum in the interstellar medium, and that hum refuses to go away. Now, let's begin with the explanation most scientists reach for first. In this view, there is nothing supernatural about the signal at all. The hum is simply the sound of a restless, weakly ionized gas, low-level turbulence, thermal motions, Countless tiny instabilities in the interstellar plasma, each one exciting waves right around the local plasma frequency, adding up to a constant background chorus. To picture this, imagine the solar wind as a river that has just plunged over a cliff at the heliopause. Beyond that boundary, the flow slows, curls, and mixes with the interstellar medium. Even far from the drop, the water is never perfectly still. In plasma terms, random fluctuations in density and electric fields, driven by background currents and the memory of distant shocks, keep stirring the charged particles. Those fluctuations naturally launch plasma waves, even when no major solar event is slamming the region. Voyager's plasma wave instrument is exquisitely tuned to this. When a big shock passes, it hears a loud whistle as the local density spikes. Between those shocks, the conventional picture says it should mostly hear silence. Instead, it hears this faint, continuous tone, as if the river beyond the solar system is always just a little bit rough. Where would that roughness come from? One idea is that the interstellar medium around the solar system is threaded by weak, tangled magnetic fields carrying slow, large-scale currents. As those fields interact with gradients in density and pressure, they can drive a simmering turbulence that never quite turns off. Even shocks from supernovae that exploded millions of years ago can leave ripples that propagate for light years, feeding small instabilities that maintain a baseline level of wave activity. But some researchers are beginning to ask a bolder question. What if this hum is not only local weather, but also the echo of the galaxy itself? Perhaps Voyager 1 is hearing interactions with large-scale galactic structures. The compressed gas at the edge of a spiral arm, a relic shock from an ancient supernova remnant, or subtle flows tied to the local interstellar cloud. In that scenario, the hum is a noise floor imprinted by the Milky Way's own dynamics, a kind of galactic background radiation in plasma form. Tonight, we're going to stay grounded, though. Before we get started on exotic headlines, it is important to see what new physics would really mean here. No one predicts hidden forces or brand new particles emerging from a 1970s spacecraft. By the end of tonight, you're going to understand that the real frontier may be more subtle. Plasma processes in weakly collisional magnetized media that current simulations still struggle to capture. In such tenuous space, particles can travel long distances before colliding. They interact more through fields than through direct hits. That makes the plasma behave in ways that are neither a simple gas nor a simple magnetized fluid. Waves can be damped in strange ways. Energy can cascade along magnetic field lines, and small anisotropies in particle motions can drive instabilities that standard fluid models simply smooth out. So when Voyager 1 reports a steady hum, one possibility is that it is exposing how incomplete those models really are. The frequency and stability of the tone might be telling scientists that the interstellar medium near the heliopause is more compressed, more structured, and more weakly collisional than expected. No one expects a single narrowband signal to rewrite plasma physics. But absolutely no one anticipates that a 23-watt transmitter running on decaying plutonium would still be forcing theorists to revise their equations in 2026. And this is where the mystery deepens, distinguishing between mundane turbulence, galactic-scale influences, and genuinely new plasma behavior demands more than clever arguments. It demands data, more spectra, more time, more context. Yet humanity has only one working microphone in this cosmic concert hall. Voyager 1 is crawling outward at about 17 kilometers per second, adding roughly 3.6 AU of distance each year. Each new measurement comes from a region no spacecraft has ever visited before. The result is a strange tension. Every extra month of hum helps map the local interstellar plasma, but also reminds researchers how blind they are to what is happening just a few astronomical units away from the spacecraft's path. If the tone changes, is that a new structure, a fading of turbulence, or a transition into a different galactic environment? If it stays the same, is that evidence of a universal background, or simply the limited reach of a single instrument? Tonight, we're going to keep following that single thread, because the hum is not Voyager's only surprise in interstellar space. When scientists compare this persistent tone with the behavior of energetic particles and cosmic rays around the heliopause, the puzzle only grows sharper, and the edge of the solar system starts to look less like a clean border and more like a tangled, dynamic frontier. The edge of the solar system looks messy in particle data and plasma waves, but the strangest clue might be the one that seems the most quiet, the way the magnetic field refuses to turn. Crossing the heliopause, scientists expected Voyager 1's magnetic compass to swing. Inside, the solar wind carries a spiral magnetic field wound up by the sun's rotation. Outside, the interstellar medium has its own field, anchored to the galaxy. The prediction is simple: new region, new direction, a sharp reorientation, a clear sign that the spacecraft has stepped beyond the solar boundary. That is not what happened. Voyager 1 saw the field strength jump, just as models suggested the interstellar field should be stronger than the stretched, fading field in the outer heliosphere. But the direction? It barely moved. The angle shifted by only a few degrees. The line on the magnetometer plot, which should have kinked dramatically, stayed nearly parallel. No one expects the compass to whisper when it should shout. To explain this, scientists reached for a powerful idea: magnetic draping. As the heliosphere plows through the interstellar medium, the external field lines cannot simply pass through the solar wind. They are forced to bend, to wrap around the nose of the heliosphere like streamlines around a blunt obstacle in a wind tunnel. In this picture, the interstellar field is stretched and aligned along the surface of the heliopause, so that near the contact region, where Voyager exited, the external field just happens to run almost parallel to the internal solar field. On paper, that sounds elegant. In simulations, it is harder. Magneto-hydrodynamic models can produce draped fields that partially line up with the heliospheric field, especially near the nose. Some runs even show regions where the angle difference is modest, but to keep that difference as small as Voyager 1 observed, over the distance and time it measured, the models often need fine-tuned choices for the interstellar field strength, its original direction, and the relative flow speed of the local interstellar medium. Pattern interrupt. What if the problem is not the draping at all, but the assumption that the fields stay cleanly separated? Some researchers have suggested that Voyager 1 might have crossed through a zone of magnetic reconnection, where field lines from inside and outside the heliosphere actually merge and exchange connectivity. In such a region, the direction could be smoothed out temporarily, erasing the stark contrast between solar and galactic fields. Others argue that the local interstellar field itself might be more twisted and irregular than the large-scale galactic average, and Voyager just sampled a magnetic anomaly, a patch where the external field already happened to resemble the solar one. By the end of tonight, you're going to understand why this is not a minor detail. The magnetic geometry controls how cosmic rays leak in, how the solar wind escapes, and how energy is traded across the boundary. Until more spacecraft probe different latitudes and longitudes of the heliopause, the true shape of this magnetic maze, and why Voyager's compass barely twitched, remains one of the mission's most persistent enigmas, setting the stage for even deeper puzzles about what lies beyond. If the magnetic field is Voyager's compass, then the cosmic rays are its weather report. Tiny, invisible particles arriving from all directions, carrying a record of every magnetic twist and turbulent eddy they've passed through. Tonight, we're going to use those particles as clues. Cosmic rays are charged. That means they do not fly in straight, noble lines through space. They spiral, they bounce, they scatter off irregularities in magnetic fields. Every bend changes how many arrive, which energies get through, and from which directions they come. By the end of tonight, you're going to understand that their intensity and spectrum are not random noise. They are an encoded map of the medium between the stars. Inside the solar system, the solar wind does more than inflate a protective bubble. It modulates cosmic rays, sweeping lower energy particles away and reshaping their paths. For decades, scientists modeled this as a gradual change with distance, then a sharp drop at the heliopause, where the solar wind yields to the interstellar flow. Expectation: a clean step. Reality: Voyager 1 showed something far stranger. As the spacecraft approached 121 astronomical units, its detectors saw galactic cosmic rays climb, not a gentle slope. A marked, sudden increase in high-energy particles from the galaxy beyond, just as the solar wind particles faded. That confirmed the heliosphere really is a shield, a magnetic umbrella that cuts down the cosmic ray flux, reaching the inner planets. No one predicts how detailed that transition would be, because it was not one jump. Some particle populations rose in distinct stages, days or weeks apart, while others lagged or behaved differently. One moment, solar-connected particles still leaked in along field lines. The next, they collapsed. Then another class of galactic cosmic rays surged, layered transitions like stepping through multiple curtains, not one solid wall. The implication is profound. Voyager was not crossing a single smooth boundary, but a sequence of regions with different magnetic connectivity to the inner heliosphere and to interstellar space. Those patterns forced a rewrite of cosmic ray modulation models. The heliopause is no longer treated as a uniform barrier. It looks patchy, corrugated, riddled with channels and bottlenecks that can open or close as the solar wind pressure changes and as turbulence rearranges the field. In some zones, cosmic rays are guided in along magnetic highways. In others, they are blocked, piled up, or diverted around folds in the boundary. This is not just an abstract victory for theory. Future deep space missions, crewed and uncrewed, will travel through these same regions, exposed to radiation levels that depend on exactly how that shielding works. Near Earth, observatories must disentangle what the galaxy is sending from what the heliosphere is filtering. Before we get started on the truly anomalous signals, remember, if the normal cosmic ray patterns already break our simplest models, what do we do when Voyager starts detecting particles that fit no pattern at all? So when Voyager starts detecting particles that fit no pattern at all, there's another, quieter fear in the background. What if the problem isn't the universe, but the spacecraft's own aging brain? In late 2023, that fear stopped being hypothetical. Voyager 1's voice went strange. For decades, engineers had read its engineering data like vital signs, voltages, temperatures, pointing, all neatly packaged into telemetry frames. Then, almost overnight, those frames turned into gibberish. The carrier signal was there. The science instruments still seemed to be collecting data, but the wrapper that tells you what you're looking at, from which sensor, at what time, was scrambled beyond recognition. Tonight, we're going to follow that moment because it shows how fragile our window on interstellar space really is. When the telemetry failed, scientists did not know if the problem was in the antenna, the transmitter, the flight data system, or something even deeper. From more than 15 billion miles away, the entire mission suddenly hinged on a few bits no longer lining up. The original plan is simple. 5 years, study 2 planets, then drift silently into the outer solar system. No one expects the computers built in the early 1970s to still be running in interstellar space. No one predicts that a single faulty chip in the flight data system memory could threaten the only continuous record of the plasma, the magnetic field, and the interstellar wind beyond the heliopause. Engineers traced the anomaly the only way they could, by talking to a half-century-old spacecraft in slow motion. A command leaves Earth, rides a radio beam across the solar system for more than 22 hours, reaches Voyager, triggers some tiny change. Then the reply takes another 22 hours to come back. 1 experiment, 2 days. If the command is wrong, there is no reset button. By the end of tonight, you're going to understand how extreme that is. Diagnosing the corrupted telemetry meant crafting sequences to probe different parts of the flight data system, then inferring which memory regions responded and which behaved like dead zones. The emerging picture, one damaged chip in a memory bank that controls how engineering data are formatted on a computer never designed to be reprogrammed in its old age. So the team did something absolutely no one anticipates during 1970s design reviews. They rewired the spacecraft in software. They moved code out of the bad addresses, split functions across surviving memory, and reconfigured which instrument outputs were routed, where all through radio commands sent from a rotating Earth to a moving target beyond the solar system's boundary. Now, let's begin to ask the uncomfortable question this raises. If a blatant glitch can scramble the telemetry packaging, what about subtler faults that nudge a sensor's calibration or flip a bit in science data without announcing themselves? Could an apparent spike in interstellar plasma density or a twist in the magnetic field direction sometimes be a wounded instrument rather than a real structure in space? Scientists guard against this by cross-checking instruments, comparing with theory, and watching for patterns that follow spacecraft temperature, orientation, or power cycles instead of external events. If a mystery only appears when the spacecraft warms up, it's probably not a new kind of interstellar wave. Yet every new anomaly is a reminder. The radioisotope generators are fading. The hardware is brittle. The software is stretched across memory cells that have been hammered by cosmic rays for nearly 50 years. And still, against those odds, Voyager's instruments keep returning data from beyond the heliopause. The resilience is astonishing, but the message is sobering. This is a time-limited experiment. Each scare, like the 2023-2024 telemetry crisis, underlines how narrow and precious our current view of interstellar space really is. The question becomes urgent. Before that window closes for good, how do we decide which of Voyager's strangest signals are artifacts of a dying spacecraft and which are clues to a boundary physics has not yet learned to describe? So here is the quiet horror behind all of this mystery. The window is closing. Voyager 1 is still hearing the faint plasma hum of interstellar space, still tasting the charged particles in that galactic wind. But the spacecraft itself is fading. Not because the mission lost interest, because the power source is literally decaying away. Before we get started on the timeline, it helps to understand what keeps a 1970s robot alive 24 billion kilometers from the Sun. Voyager carries 3 radioisotope thermoelectric generators, RTGs, each one a hot brick of plutonium-238 surrounded by thermocouples. As the plutonium decays, it releases heat. The temperature difference between the hot core and the cold of space is converted directly into electricity. No moving parts, no solar panels, just nuclear warmth holding back the dark. Designed for a 5-year mission to study 2 planets, those RTGs were supposed to power a short grand tour and then slowly fade as the spacecraft drifted into the outer solar system. Reality is harsher and stranger. Every year the RTGs produce a little less electricity, about 4 watts lost per year across the system, forcing engineers into a kind of slow-motion triage. No one expects a 1977 power budget to still be getting edited in the 2020s. That triage is brutal. Heaters on some instruments have already been turned off, leaving hardware to endure temperatures far below design specs. Non-essential systems, cameras, tape recorders, many engineering functions were shut down years ago. What remains is a skeleton crew of science. The plasma wave instrument that hears the interstellar medium, the magnetometer that feels the galactic field, the cosmic ray detectors that count high-energy particles from beyond the solar boundary. Tonight, we're going to follow that power curve into the future. Projections suggest that by the late 2020s, there will not be enough electricity to run all of those remaining instruments at once. Engineers will have to decide which senses to keep and which to blind, cycling instruments, sacrificing redundancy, squeezing every last bit of voltage from a dying nuclear heart. By the end of tonight, you're going to understand the real end of the Voyager mission, not a dramatic explosion, not a collision, just a slow dimming. Most estimates put the final cutoff in the early to mid-2030s. Somewhere in that decade, the RTGs will no longer supply enough power for any science instruments. The spacecraft will still fly on, its golden record still attached, but it will be deaf and mute, a silent relic drifting through the galaxy. And yet, in those remaining years, Voyager 1 is not just coasting through empty space. It is still inside the local interstellar cloud, moving through a region where density, magnetic field strength, and cosmic ray pressure may all change subtly over tens of astronomical units. If the plasma wave instrument and magnetometer survive just a little longer, they can trace those gradients, giving scientists a 3-dimensional sense of how the interstellar medium wraps around our solar system, like a shifting, invisible weather pattern. Every extra year of data is a gift, another solar cycle's worth of shocks punching through the heliopause, another set of measurements of that persistent low-level hum, another chance to see whether those unexplained density spikes and magnetic kinks repeat, evolve, or vanish with distance. No one predicts a miraculous extension. Absolutely no one anticipates a new RTG appearing out of nowhere. The clock is running. So the urgency sharpens. Which mysteries can actually be solved before the instruments go dark, and which questions will be left hanging, frozen into a data stream that ends mid-sentence, while Voyager continues on into regions no living spacecraft will visit again for generations. So, the urgency sharpens. But before the power runs out, there's a deeper question hiding underneath all the weird data. What does it even mean to say Voyager has left the solar system? The first surprise is that there is no single edge. There are multiple boundaries nested like invisible shells, and which one matters depends on what is being asked. If the concern is the sun's gravity, The solar system extends absurdly far. Its pull dominates over passing stars out to tens of thousands of astronomical units into the realm of the Oort cloud, where comets drift in a dark, distant reservoir. Those icy bodies are still bound to the sun long after the planets are a faint memory, but gravity is only one way to draw a line. In terms of the space environment, the more meaningful transition is where the solar wind loses and the galaxy's gas and magnetic field win. That is the heliopause. Inside, the sun's plasma bubble and magnetic field set the rules. Outside, the interstellar medium does. When Voyager 1 crossed that boundary in 2012, when the solar wind particles dropped and interstellar plasma waves rose, scientists had a practical marker. This is interstellar space. Expectation: a neat spherical bubble with a crisp surface around 90 to 100 AU. Reality: Voyager 1 hits the termination shock at 94 AU, then the heliopause at 121 AU. Voyager 2 crosses at different distances. No one predicts that the edge would be asymmetric, lumpy, and mobile. By the end of tonight, you're going to understand why every textbook diagram had to be redrawn. Those simple cartoon bubbles gave way to something stranger. Data from both spacecraft, combined with energetic particle and magnetic field models, now point to a distorted, possibly croissant-shaped heliosphere, with two thick lobes trailing behind the sun. The nose region where the solar wind slams into the galactic headwind is layered and turbulent. The tail is dragged and twisted by the interstellar magnetic field and the flow of the local interstellar cloud. The solar system is not a tidy sphere. It's a stressed, sculpted bubble being pushed from all sides. Tonight, we're going to sit right on that frontier. Voyager's measurements show that the transition is not a single wall but a series of sheaths and gradients. Energetic particles fade in steps. Plasma density jumps in stages. Magnetic field directions rotate slowly instead of flipping like a switch. The old picture of a sharp, static edge has been replaced by a living boundary that swells and wrinkles with the 11-year solar cycle and with whatever the galaxy throws at it. Here's the pattern interrupt. The edge of the solar system is no longer a line on a page. It's a negotiation zone, a contact surface between one star and the wider Milky Way. And for the first time in history, a human spacecraft has dipped a sensor into that cosmic handshake, revealing that the place where our solar wind ends and the galaxy begins is far more intricate and far more mysterious than anyone expected. That cosmic handshake is not unique. Every star does this. Every star plows through the galaxy, blows a wind, and carves out its own invisible bubble in space. Around the sun, it's called the heliosphere. Around other stars, scientists call it an astrosphere. Think of an astrosphere as a scaled-up version of Earth's magnetic shield. Your planet's field deflects a fraction of charged particles from the sun. The heliosphere does the same thing for the entire solar system, pushing back the galaxy's cosmic rays. Out there, beyond our neighborhood, other stars throw out their own stellar wind and inflate their own protective cavities. Inside the bubble, the star's wind dominates. Outside, the interstellar medium and the galactic magnetic field take over. Here is the problem. Those bubbles are light years away. No one expects to park a probe next to a random red dwarf and sample its boundary. No one predicts a Voyager-style mission to Alpha Centauri with current technology. So how do you understand the astrospheres of other stars when you cannot touch them? Now, let's begin. Voyager becomes the template, By the end of tonight, you're going to understand that when this spacecraft crossed the heliopause, it did more than leave the solar system. It provided the first in situ blueprint for how any stellar wind slams into the interstellar medium. The layered increases in plasma density, the strange alignment of the magnetic field, the way cosmic rays surged and solar particles dropped off in steps instead of a clean jump, all of that is a worked example of stellar wind physics at a boundary layer. Change the star and the bubble changes. A young active star with a furious wind can inflate a huge astrosphere, pushing galactic cosmic rays farther back and giving planets a deeper shield. A weak, fading star might barely hold off the interstellar medium. Denser interstellar clouds squeeze bubbles smaller. Stronger galactic magnetic fields can distort them into teardrops, crescents, or even fragmented shapes. For a planet on the inside, that geometry is not just an abstract diagram. It sets the radiation environment at the surface. This is where Voyager's weirdness matters. Those unexpected layers just beyond the heliopause show that boundaries can trap and channel particles instead of simply blocking them. The nearly parallel magnetic field lines suggest that interstellar fields can drape and wrap around a star's bubble in subtle ways. So when astronomers see faint astrospheric absorption lines in the ultraviolet, or detect radio emissions hinting at stellar winds around distant planets, they are not just fitting simple spheres. They are now forced to imagine tangled, structured interfaces. Absolutely no one anticipates that a 1970s spacecraft would become a Rosetta Stone for exoplanet habitability. Yet every anomaly it discovered hints that many astrospheres are intricate, leaky, and dynamic, shaping which worlds in the galaxy get a gentle rain of radiation and which stand under a constant cosmic storm. Those tangled, leaky astrospheres raise a new question. If a 1970s spacecraft accidentally revealed all of this, what happens when a mission is built from the beginning to plunge straight through the boundary and keep going into interstellar space? Now, let's begin with an idea that sounds like science fiction, but is sitting in real proposal documents: Interstellar Probe. Not a grand tour of the outer planets that just happens to escape, but a mission whose primary goal is to leave the solar system fast. Using a powerful launch vehicle, a close solar flyby, and possibly a Jupiter assist, scientists sketch a spacecraft that could reach the heliopause in 20 to 25 years, instead of 35. Tonight, we're going to follow that imagined trajectory. This interstellar probe would carry plasma instruments that make Voyagers look ancient. High cadence detectors could track the solar wind thinning, the temperature dropping, and the turbulence changing almost kilometre by kilometre. Vector magnetometers with far better sensitivity could watch the field twist as the spacecraft crosses the heliopause, resolving whether that strange alignment Voyager 1 discovered was a local fluke or a signature of how the interstellar field drapes around the heliosphere. Beyond the boundary, new tools unlock new views. Energetic neutral atom imagers looking back at the solar system from the outside could build global maps of the heliosphere, not as a guess from inside but as a direct image. Higher resolution particle detectors could separate local interstellar cosmic rays from those sneaking in through magnetic cracks. By the end of tonight, you're going to understand why scientists are obsessed with seeing that interface from both sides. No one predicts Interstellar Probe will just sprint past everything. Along the way, it could fly by distant Kuiper Belt objects, sampling how the solar wind behaves around small, icy worlds sitting near the edge. With the right trajectory, It might even skim regions where Oort cloud bodies begin to dominate the mass distribution, measuring dust, plasma, and magnetic fields in places no spacecraft has ever touched. The crucial test comes at the heliopause itself. Voyager 1 inferred plasma properties from wave tones in the dark. Its own plasma instrument had failed decades earlier. A next-generation probe, crossing at a different latitude and during a different solar cycle, could directly measure the density, temperature, and flow of both the solar wind and the interstellar medium. Expectation versus reality would be laid bare. Is the boundary smooth, rippled, or shredded into filaments? Does the plasma hum extend everywhere, or was Voyager flying through a rare, compressed region? And Interstellar Probe does not have to fly alone. Other concepts imagine swarms of small probes or solar sail-powered craft riding sunlight to high latitudes above and below the planets. Instead of one lonely line through space, dozens of trajectories could pierce the heliosphere at multiple angles, turning a two-dimensional sketch into a three-dimensional map of the boundary and the surrounding interstellar medium. Suddenly, Voyager's anomalies are not dead ends. They become design requirements. Instruments are tuned to the unexplained hum. Trajectories are chosen to cross where the magnetic field should twist the most. Power systems are built to last long enough to see the solar wind breathe over an entire cycle. Absolutely no one anticipates this when Voyager launched, but those puzzling measurements are now steering the next generation of interstellar explorers. The real twist comes when these future scouts start sending back data that disagree not just with Voyager but with each other, forcing a decision about what, exactly, the edge of the solar system really means. So, after all of that, it's tempting to say Voyager has broken physics. Mysterious hums, layered boundaries, densities and fields that refuse to line up. It sounds like the solar system is hiding a portal in plain sight, but in science, phrases like "cannot be explained" have a very specific meaning. They almost never mean the laws of nature just stopped working. They mean something quieter and in some ways more interesting. The data do not yet fit neatly into the models that scientists are using. The equations of plasma physics still apply. Magnetohydrodynamics still rules. What's in question is how to stitch those equations together in a region that no one has ever sampled before. Before we get started on wild speculation, it helps to remember where most researchers actually are. The dominant view is not that Voyager 1 has discovered new forces beyond the standard picture. The dominant view is that this spacecraft has finally flown into a regime of space where the familiar rules of plasma and magnetic fields interact in ways that are hard to calculate, but not impossible in principle. Think about what Voyager is trying to traverse: the solar wind flowing out from the sun, the local interstellar medium pushing back as a galactic headwind, a boundary that is not a clean shell, but a tangled, three-dimensional contact zone filled with weakly collisional, magnetized, turbulent plasma. Now add time. The solar cycle is changing, the wind pressure is breathing, the external medium is not uniform. By the end of tonight, you're going to understand why absolutely no one anticipates a simple diagram to survive contact with that reality. From that perspective, the anomalies look less like magic and more like a bookkeeping problem at the edge of the solar system. The persistent plasma hum, probably a natural resonance of interstellar electrons driven by background disturbances but sampled along a single, narrow trajectory. The higher-than-expected density just beyond the heliopause, likely compression where the solar wind's momentum is transferred to the interstellar flow in a geometry more complex than early models assumed. Here's the pattern interrupt. The real excitement is not in tearing up physics textbooks, it's in watching familiar laws play out in an unfamiliar theatre. Weakly collisional plasmas can generate waves, shocks, and filaments that emerge from simple equations but look anything but simple in practice. Simulations struggle, not because the laws are wrong, but because the combination of turbulence, magnetic reconnection, and evolving boundaries is brutally difficult to resolve. And Voyager is not helping by being generous with data. It is one spacecraft, one path. Instruments designed in the 1970s with limited angular coverage and energy ranges trying to decode a three-dimensional, time-dependent structure from a single, slowly moving line through space. No one expects definitive maps from that. No one predicts clean answers. Yet that is exactly where the mystery remains sharp. Even if no new fundamental forces are needed, Voyager 1 is still detecting patterns and structures that current simulations cannot reproduce simultaneously. The layered cosmic ray gradients, the magnetic field rotations, the slow evolution of that interstellar hum. The laws are familiar, the behavior is not. Now, let's begin to ask what those stubborn mismatches are actually telling us about the shape of the heliosphere itself. Those stubborn mismatches are telling scientists something else as well. This isn't just a machine in the dark, it's a messenger. Before we get started on what those signals mean for the shape of the heliosphere, pause and remember what Voyager 1 is actually carrying into interstellar space. This spacecraft does not travel alone. Bolted to its side is a copper phonograph record, plated in gold, spinning silently through a medium thinner than the best vacuum on Earth. The golden record is a time capsule from one small world, a curated snapshot of an entire solar system civilization compressed into grooves and diagrams and a single hopeful instruction. Play this. On it are greetings in 55 human languages, from ancient Akkadian to modern English, a child's voice saying hello, a Chinese speaker wishing whoever finds it peace. There are messages from the UN Secretary-General and the President of the United States, not just representing governments, but trying to speak for a species that has only just begun to understand the space around its own star. There is music. Bach's Brandenburg Concerto and Beethoven's String Quartet, written for candle-lit rooms and wooden instruments now drifting beyond the heliopause. Beside them a Navajo night chant, a Japanese shakuhachi piece, and Chuck Berry's Johnny B. Good, a 1950s rock and roll track currently flying through a region where the interstellar plasma hums at a few hundred hertz. Designed for record players and radio stations, now embedded in a spacecraft that measures magnetic fields and solar wind shock fronts. There are natural sounds, thunder rolling through Earth's thick atmosphere, waves breaking on a shoreline, wind in trees, a heartbeat, a mother's first words to a newborn, whale songs, recorded in the 1970s, now further from the oceans than any molecule of seawater has ever travelled. No one expects a humpback to be heard in interstellar space. No one predicts that those calls would share a vehicle with instruments mapping cosmic ray gradients beyond the sun's protective bubble. There are 115 images encoded as analog signals, children eating ice cream, diagrams of DNA, a page from Newton's Principia, a supermarket, a snow-covered mountain range, a launch pad, a sunset over the Pacific, a map of the solar system with the planets arranged in order and a line showing Voyager's path out, past the boundary where the solar wind yields to the galactic wind. Now, Let's begin to feel the contrast. A human-made artifact with 1970s circuits and tens of kilobytes of memory is drifting through a region whose magnetic mazes and plasma waves modern simulations cannot yet reproduce. By the end of tonight, you're going to understand why its data is so confusing, but at the same time, it is carrying a whisper that says, to anyone and anything beyond, we were here. This is the same mission doing two things at once. As a scientific probe, Voyager 1 is measuring densities, fields, and particles challenging every model of the heliosphere's edge. As a cultural probe, it embodies a deeper drive, the desire of a young, technological species to be known in a universe that has not, so far, answered back. Here's the pattern interrupt. When those unexplained plasma tones arrive at Earth, they are riding on the same carrier wave that could, in principle, someday bring a reply to that record. The mystery signals and the message in a bottle are inseparable, and to understand what Voyager 1 is really detecting out there, the story has to return to the boundary itself and to the strange, layered frontier it discovered when it first stepped into interstellar space. So now the story has to return to the boundary itself. To make sense of those strange signals, you need a new mental map of where Voyager 1 actually is and what it fought through to get there. Tonight, we're going to fly there in your imagination. Not with a rocket, but with a guided tour from the inner solar system outward all the way to that rippling frontier where our star and the galaxy collide. Now, let's begin. Picture yourself near the Sun inside the orbits of the familiar planets. Here, the solar wind is young and fast, a supersonic outflow of plasma racing past Earth, Jupiter, even Saturn. Every textbook diagram used to show this as a simple expanding bubble, smooth and mostly spherical, fading gently into interstellar space. But keep going outward with Voyager, past Uranus, past Neptune, past Pluto's elongated path. The wind is still blowing, but it's slowing, piling up against the thin interstellar medium. Models once placed the termination shock at maybe 75 to 90 astronomical units. Voyager 1 does not find it there. It keeps going. 90, 94. Only then does the shock appear, far beyond what most scientists were willing to bet on. Cross that shock with the spacecraft. The solar wind drops from supersonic to subsonic. The flow becomes turbulent, filled with eddies and tangled magnetic fields. Here, Voyager discovers something else the old bubble diagrams never hinted at: layers in the radiation. Galactic cosmic rays begin to rise, but not smoothly. They surge and stall in sharp steps, as if the boundary is made of overlapping shells, not a single clean line. Move farther out, toward the heliopause. This was supposed to be the crisp edge, the place where solar wind pressure and interstellar pressure balance. Instead, Voyager 1 finds a boundary that behaves like a warped, leaking membrane. Cosmic rays from the galaxy jump up in sudden plateaus. Solar particles drop in uneven stages. No one predicts that the magnetic field on the other side will still be aligned almost as if it belongs to the Sun. Step across with Voyager into interstellar space. Particle counts say you're outside, cosmic rays say you're outside. But the magnetometer whispers a different story. The field direction barely twists. Then the plasma wave instrument speaks up. It hears a denser-than-expected interstellar plasma compressed as if the heliosphere has ploughed a bow wave into the galaxy, and on top of that, a persistent, faint hum, continuous vibrations of the interstellar medium, not just the brief screams of solar storms. By the end of tonight, you're going to understand why that matters, because the picture in your head can no longer be a neat bubble with a single line around it. Replace it with a distorted, rippling boundary, threaded with magnetic ropes, streaked with density gradients, riddled with channels where particles leak in and out. In this new map, the solar system is not an island, it's an interface zone, a contact surface where stellar wind and galactic environment wrestle in real time. And once you see that, Voyager's unexplained signals stop being isolated anomalies and start looking like clues to a frontier far stranger than absolutely no one anticipates. The next step is to take this map, hold it up against Voyager 1's latest detections and ask, what exactly is this frontier trying to tell us? So, what is this frontier trying to tell us? To answer that, you have to face a harder truth. The reason Voyager 1 is detecting things in interstellar space that cannot be explained is not one thing. It is a perfect storm of distance, aging hardware, wild physics, and limited perspective. Start with distance. Voyager 1 is more than 15 billion miles from the Sun. Its transmitter pushes out only about 23 watts, less than a refrigerator bulb. By the time that signal reaches Earth, it is unimaginably faint, buried in cosmic noise, pulled out by giant radio dishes and careful averaging. That means every wiggle in the data is subtle, a tiny plasma wave, a small glitch in an instrument, a numerical artifact in the processing pipeline. They can look eerily similar. Then there are the instruments themselves. This spacecraft was built in the 1970s, with memory measured in kilobytes and detectors designed for a 5-year tour of the outer planets, not decades in interstellar space. Sensors have aged. Calibrations drift. Some instruments failed years ago, leaving gaps that other instruments must cover indirectly. When scientists see a persistent plasma hum or a sudden change in energetic particles, the question is immediate. Is this the local interstellar medium, or the limitations of a tired machine? Often it could be either. Layered on top of that is the medium Voyager is flying through. Interstellar space is not empty. It is a turbulent, magnetized plasma, threaded with fields, waves, and shocks across an enormous range of scales. Microscopic instabilities jostle individual particles. Global flows reshape the entire heliosphere. Tonight, we're going to focus on that collision of scales, because it is exactly where many of Voyager's anomalies live, at the intersection of local plasma physics, solar wind history, and galactic environment. And remember, there are only 2 sampling points, Voyager 1 and Voyager 2, moving along 2 narrow trajectories through a vast 3-dimensional structure. No one predicts a neat, uniform boundary under those conditions. A sharp jump in plasma density here, a layered cosmic ray transition there, a magnetic field that refuses to twist as models demand. Each could be a local filament, a folded current sheet, or a global property of the heliosphere. With just 2 paths, those possibilities are hard to untangle. Even our best supercomputer simulations struggle. They must bridge from electron-scale physics to the entire solar system, from rapid plasma waves to million-year galactic flows. Resolution is limited, approximations are necessary. So when Voyager 1 hears a constant, faint interstellar hum or measures a surprisingly compressed plasma just beyond the heliopause, it is often probing regimes where theory, simulation, and observation do not yet line up. By the end of tonight, you're going to understand that this is not a failure. This is the point. Voyager is scientifically valuable precisely because it lives where our models break. Every unexplained signal is a constraint. Every anomaly is a demand that the equations be rewritten. So the real answer is this: Voyager 1 is detecting things we cannot fully explain. Not because the universe is unknowable, but because we are catching our own understanding mid-upgrade, right at the frontier where new knowledge is being forged. Now, let's begin to ask the dangerous question. What if even these upgraded models are still missing something fundamental about the space just beyond our solar system? So now, step back and look at the whole arc you've just crossed. 2 spacecraft launched in 1977, designed for a modest 5-year mission to skim past 2 giant planets. No one expects that quick grand tour of Jupiter and Saturn to turn into a 50-year odyssey that carries Voyager 1 beyond every known boundary of the solar system. Yet, that is exactly the journey you followed. You watched the mission slingshot past the outer planets, stealing momentum from their gravity, trading orbital energy for speed. From Io's volcanoes to Europa's hidden ocean, from Saturn's sculpted rings to Neptune's dark storm, the spacecraft rewrote what the word planets even means. Then the cameras dimmed, the power dropped, and the real mystery began, the long, cold plunge into the outer heliosphere, toward a boundary scientists once drew with chalk and equations instead of data. Along that path you saw the first crack in the old model, the termination shock, not at 75 or 80 astronomical units, but way out at 94. The solar wind did not slow where it was supposed to. The shock was distant, irregular, misbehaving. That single crossing announced that the neat, spherical heliosphere in the textbooks was an illusion. Then came the layered, leaky, cosmic ray shield. Instead of a smooth fade from solar particles to galactic ones, Voyager 1 discovered stacked regions where intensities jumped, stalled, and reversed. A boundary that was supposed to be simple behaved more like overlapping curtains of charged particles fluttering in an invisible wind. You watched the controversial heliopause crossing in 2012, when the plasma density, the energetic particles, and the magnetic field all told slightly different stories. One instrument said outside, another whispered not yet. The stubborn magnetic alignment on both sides of the heliopause shattered the idea of a clean magnetic flip, hinting that the interstellar field is being dragged, twisted, and draped around the heliosphere in ways models never captured. Beyond that, the compressed interstellar plasma, denser than expected, ringing like a struck bell, forced a redefinition of what interstellar space means. The eerie plasma hum, a constant low-level tone instead of silence, revealed that even the dark between the stars has weather, waves, pressure changes, distant storms, and the evidence for turbulence and layered boundaries showed that the edge of the solar system is not a line but a tangled, dynamic interface. By the end of tonight, you're going to understand that every one of these discoveries tore away a piece of the old picture. The heliosphere is now multi-layered in your mind, a solar wind bubble with shocks, sheaths, draped fields, and turbulent skins. Interstellar space is no longer empty. It is a flowing medium that can be compressed, heated, and stirred. And single-point measurements from a lonely spacecraft now read, to you, like sampling one droplet in a storm and inferring the entire cloud. This is the personal transformation hidden inside all the data. Before Voyager, this frontier existed only on theorists' chalkboards. Tonight, we're going to treat it as a real, physical place that you can mentally walk through, complex, shifting, and still resisting easy explanation. The dangerous question now is not whether the old models were wrong. It is whether even this upgraded, layered view is still far too simple for what truly waits beyond the heliosphere. If the heliosphere is stranger than expected, the consequences reach all the way back to your lungs, your electronics, and the future of human travel. The shape and strength of this invisible bubble are not just academic details, they help decide how much of the galaxy's radiation actually reaches Earth. Now, let's begin with home. The sun's magnetic field, frozen into the solar wind, wraps the solar system in a vast, protective cocoon. Galactic cosmic rays, high-energy particles from distant supernovae and other violent events, slam into that cocoon. The heliosphere deflects some, slows others, and modulates how many penetrate toward the inner planets. When the solar wind is strong, the shield thickens and the flux of galactic cosmic rays at Earth drops. When the wind weakens, the shield thins and more radiation reaches the atmosphere. Those particles are not just an abstract hazard, they break apart molecules high above you, influencing atmospheric chemistry and seeding ionization that can nudge cloud formation. They increase radiation doses on polar airline routes and bombard satellites and astronauts in low Earth orbit. By the end of tonight, you're going to understand that every unexpected density spike Voyager 1 has detected out in interstellar space is indirectly a clue about how that flux might change over centuries and millennia. Pattern interrupt. This is not only about Earth. Imagine a crewed vehicle, decades from now, pushing beyond Mars. Once you leave the thickest part of the heliosphere, the radiation environment stops being dominated by the Sun and starts being dominated by the galaxy. Long-duration missions, nuclear electric drives, even early interstellar precursors will live or die by how well mission designers can predict those gradients in particle intensity, those magnetic wrinkles, those compressed regions Voyager has already found. No one expects a 1970s spacecraft to become a pathfinder for human radiation safety, but that is exactly what is happening. The layered structure at the heliopause, the odd cosmic ray profiles, the persistent plasma hum in interstellar space, these are the first real measurements of the environment future crews will face when the solar wind's protection finally fades behind them. Zoom out again. Our Sun is not unique. Other stars blow their own stellar wind bubbles, astrospheres, into the interstellar medium. Some are strong and inflated, others are weak and crushed by dense galactic gas. For an exoplanet orbiting within one of these systems, that difference can be the line between benign drizzle and constant radiation storm. A thick astrosphere can shield a habitable zone world, preserving atmospheres and surface chemistry. A thin one might leave even an Earth-like planet stripped and sterile. Voyager's strange data, then, are not just about one boundary. They are a template for all such boundaries, a way to read which distant planetary systems might actually be friendly to life. Before we get started on ranking exoplanets by oceans and temperatures, the galaxy forces a more fundamental question. How good is their shield? Philosophically, this changes what home means. The solar system does not end at Neptune or Pluto or even the last icy rock in the Kuiper belt. It ends where our star's influence finally negotiates a truce with the galaxy. That boundary is mobile, sculpted by solar cycles and the local interstellar wind breathing in and out over tens of thousands of years. No one predicts that a magnetic frontier, tens of billions of kilometers away, would become part of the definition of Earth's habitability. Yet here we are, Voyager's journey makes that abstraction visceral. A small, aging spacecraft has physically crossed the line where our protective bubble gives way to the wider galactic environment. The mission is not just a technical triumph of navigation and engineering, it is the first survey of the terrain that any future interstellar probe, and one day, perhaps human descendants, will have to traverse. Tonight, we're going to treat Voyager not only as a messenger from interstellar space, but as an early scout of our species' possible road into the galaxy. The mystery now is not whether we can follow, it is what else might be waiting in that dark, humming medium between the stars. So imagine this road into the galaxy reaching a quiet bend in the 2030s. Somewhere in a dim control room at NASA, a screen updates one last time. A new line of numbers appears from a point more than 20 billion kilometers away. It is not a dramatic image, not a final photograph of planets or rings. It is a measurement, perhaps a tiny change in interstellar plasma density. Perhaps one more data point in the magnetic field, nudging our models of the solar boundary by a fraction. Then, nothing new. The antenna on Earth keeps listening, the spacecraft keeps transmitting as its power dwindles, but at some moment the last truly meaningful bit of science data arrives. The next day, the plots look the same. The next week, the noise floor rises. The next year, the carrier itself may fade into the background hiss of space, designed for a 5-year mission to study Jupiter and Saturn. It will have spoken to Earth for nearly 6 decades. No one expects that. No one predicts a 23-watt transmitter with less memory than a cheap calculator to keep a conversation going from interstellar space. And absolutely no one anticipates that the final whisper will be about the pressure of a medium thinner than any vacuum humans can create. After that last signal, Voyager does not stop. The spacecraft simply becomes silent. It continues on a 40,000-year trajectory toward a dim star in the direction of the constellation Ophiuchus, carrying a golden record etched with sounds and images of oceans, wind, languages, and music. A tiny archive of a young species that once clustered around a yellow star and wondered what lay beyond its heliosphere. Before we get started on what future probes might discover, it is worth pausing on how much this one has already given. From the volcanic fountains of Io to the braided rings of Saturn, from Miranda's shattered face to the supersonic winds of Neptune, this mission redrew the map of the outer solar system. Then it crossed the termination shock, threaded the layered shell of the heliosphere, and stepped into the faint hum of the local interstellar medium. The stream of data will end. The work will not. By the end of tonight, you're going to understand that Voyager's archive is not a finished story but a reference library. Decades from now, scientists will still be mining those plasma waves and cosmic ray counts, testing new simulations of the heliopause, reinterpreting that persistent interstellar hum in the light of missions not yet launched. In that sense, the last signal is less a period than a handoff. The silence after Voyager is a cliffhanger of a different kind. Not a promise of the next plot twist, but an open invitation to whoever comes next to push the boundary outward. The question is no longer whether the signal will stop. The question is, who will answer it? So tonight, somewhere 15 billion miles from here, the spacecraft is still doing its work. The plasma hum is still there. The magnetic field is still twisted into shapes the models cannot explain. The cosmic rays are still arriving at densities no one predicted. Voyager 1 is alone, running on a battery the size of a small refrigerator, sending back data that nobody on this planet entirely understands yet. There is something steadying in that. The spacecraft does not need to be watched to keep working. The interstellar medium does not stop being strange when we look away. The boundary of the solar system is being measured right now by an instrument designed before most people watching this were born. And that instrument is patient enough to keep listening long after this video ends. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.